The purpose of today's lab is to determine the value of Coulomb's constant. We know what that value is, right? 8.99 times 10 to the 9. But we're going to try to show that, in fact, that is the real value of Coulomb's constant using this computer simulation. The problem, always phrased in the form of a question: what is the experimental value of Coulomb's constant? You're going to have three variables, of course. One manipulated variable. Okay, it's the one that you change. And hopefully that becomes relatively obvious to you as we work through the procedure here. You're going to have one responding variable, and again, hopefully that becomes fairly obvious to you as we work through the procedure. And there are really an infinite number of control variables. How many do I expect you guys to list? Well, the important ones. If there's one important one, then list one. Or if there's two important ones, then list two. If there's three important ones, list three. The temperature of the air has to remain constant. Don't list that one. Okay, list the ones that are critical to this lab working out. Those should hopefully become obvious to you as we work through this procedure here. When you click on the link on the applet under Google Classroom, you're going to see a diagram that appears at the top of this page. The charges are initially going to be one. Notice the charge here is measured in microcoulombs. You're going to, when you do a calculation, want to convert that back to coulombs, right? A microcoulomb is 10 to the minus 6. They're initially going to be 1 microcoulomb each. I want you to change one or both of those values so that your charges are different from one another. I don't care if they're 1 and 5 like I have up here, or whether they're 1 and 7 or 2 and 3. Okay, whatever you want to do, just make the charges different from one another. But once you make the charges their values, keep those values the same for the rest of the experiment. Now, you're going to see here down at the bottom, there's a R value, which is the distance that separates the two charges. In this case, 0.0990 meters. You're going to record that value. You also see a value of force. In fact, there's two values of force, F1 and F2. They should be the same value, right? Because if object A applies a force on object B always applies an equal and opposite force on object A. You're going to record one of those forces. It doesn't matter which one, because they're both going to be the same. And then you're going to change the value of R. You're going to manipulate the value, the separation distance between these two charges. And you're going to do that by clicking and dragging one or both of the charges. I don't care exactly how you do this. Okay? Move this one to the right, move this one to the left, move this one to the right. Move them both. I don't care. Change the distance that separates those two charges. So basically, that's the experiment. Okay? Change the value of Q so that it's different than the default values and different from one another. Record the value of R and F, and then change the value of R and see what F does in response to that. Do it at least 10 times so that you have a data table like this. Two charges that stay the same throughout the whole thing, and then 10 separation distances and 10 values of the electric force. What do you think you're going to do with that table? What do you always do with the table? Yeah? Plot a graph. What's our graph going to look like? What's going to be on our y-axis? Force. What's going to be on the x-axis? Okay, it's the separation distance, the value of R. So we're going to plot it like this. Now, you're going to, when you plot this graph, use words as opposed to symbols like I'm using. I'm just trying to save a little bit of time here. When you plot that graph of force versus separation distance, or force as a function of separation distance, the graph that you get should look like this. I want you to plot the points as a scatter plot and then include a trend line. Because this is computer-generated data, the data should be perfect, right? So your trend line should be perfect as well. If your trend line doesn't fit perfectly, then you pick the wrong trend line. Clearly, it's not going to be a linear trend line, right? Pick the trend line that fits the best. And you should find one that fits very, very, very well. You do not need to display the equation for this, because mathematically we're not going to do anything with this graph. We're just going to look at this and say, oh, that looks like a relationship. F is related to 1 over r squared. Remember, that's what Coulomb noticed when he plotted that graph, right? F is related to 1 over r squared. So, how are we going to get some numbers from this? How are we going to do an analysis with this graph? Well, we're actually going to change the graph. instead of using this graph, this curved line graph that's a little bit more difficult to deal with, we're going to change it into a straight line graph. Now, how are we going to do that? Well, if we know the relationship, or we're hypothesizing that the relationship is f is related to 1 over r squared, then we're going to try plotting a new graph of f versus 1 over r squared. So to do that, of course, we have to create a new table. Force is still the same in the second column, but in our first column, it's now going to be 1 over the separation distance squared. So let's say your first separation distance was 10. 1 over r squared would be 1 over 10 squared. Okay? Square the value of 10, you get 100. Take the inverse of that, you get 0.01 would be 1 over r squared. Make sense? Guess what we're going to get when we plot that graph? It's going to be a straight line. That's going to happen every time. Every time if we look at a graph and we find that the relationship is f is related to 1 over, or y is related to 1 over x squared, if we plot f or y versus 1 over x squared, it'll be straight. If the relationship is, let's say, kinetic energy is related to v squared, then we would plot ek and v squared to get a straight line. If we found the relationship was for centripetal force, F is related to or equal to mv squared over r, how would we get a straight line? Plot F versus 1 over r. Make sense? You get a straight line by taking the relationship from the equation and then putting that relationship on the x-axis of your new graph. So in this case, F is related to 1 over r squared. We know that because of the shape of this graph. So we're going to plot F versus 1 over r squared, and that's going to straighten it out for me nicely. Now the benefit of that, we've done this before, right? We did this with our first lab. The benefit of that is that we can determine what the slope and, if necessary, the y-intercept represent here. Okay, what's the equation for this graph? Y is equal to mx plus b. The y-axis is electric force, m is the slope, x is 1 over r squared, and you're going to find the value of b. It may not be exactly 0, but it's going to be very, very small compared to the numbers on the y-axis. Okay, somebody in the last class had a number on the y-axis of 1,000, like 1,000, 2,000, 3,000, 4,000. Your numbers could be different depending upon how you collect data, right? Their y-intercept was 8. Well, 8 relative to 1,000 is basically 0, right? So the y-intercept will either be 0 or it will be so close to 0 that it just doesn't matter. Now, in the last lab that you did, sorry, the first lab that you did, you had to derive an equation with those variables in it. Nice thing about this one is that equation is already given to us on our data sheet. What equation on our data sheet has both F and r squared in it, in the context of electricity, that is? Yep. Good. F is equal to k q1 q2 over r squared. Good. There's another one, right, for Newton's law of universal gravitation, but of course we're going to pick the one that's relevant to this topic, this lab. Now we're going to cross off things that appear in both. F appears in both. R squared appears in both. What am I left with? The slope is kq1, q2. Well, you've already displayed the equation on this graph from Google Sheets, so Google Sheets has told you what the value of the slope is. You've recorded the value of q1 and q2, although you've recorded them in microcoulombs, and when you do the calculation here, you want to be in coulombs. Solve for the value of k, which is exactly what you were trying to accomplish with this. What's the conclusion? Well, your conclusion would normally relate back to a hypothesis, right? But a hypothesis would always relate back to a problem. Okay? Usually we'd say if we had a hypothesis, restate the hypothesis, then accept or reject the hypothesis. We don't have a hypothesis here. That's okay. If the hypothesis relates back to the problem, let's just relate our conclusion back to the problem. In other words, the problem was, what is the value of this of Coulomb's constant, K? The value of Coulomb's constant is, write it down, whatever you got. And then justify it. How do you know that? I know this because whatever. Okay, I don't expect you to give me this entire analysis again, but just give me a brief summary of that analysis in your conclusion to tell me exactly what you did.